Not all forces are horizontal. Let's look at how to treat forces that are not horizontal. So here we have someone pulling on a box, but the rope is not horizontal. It's actually pointing above the horizontal. The free body diagram would look like this, with a force tension up and to the right, a weight force straight down, a normal force straight up. And in this case, let's also add friction. Let's define the tension as being at an angle theta above the horizontal. Now, just like for velocity vectors, a force is a vector as well. And that force vector has a magnitude and a direction. And so let's look at this force tension that's at an angle theta above the horizontal. It will have both an x component and a y component. So think about those two sides of that triangle. This side will be the x component of the tension, and this side over here will be the y component of the tension. Now, the adjacent side goes with cosine. So if you remember, the cosine of an angle is adjacent over hypotenuse. And in this case, it would be the cosine of the angle. Adjacent would be the x component of our tension. Then the hypotenuse is the full magnitude of the tension. So if I then multiply by Ft on both sides, I'll have Ft times the cosine of theta would equal Ftx. I can do the same sort of thing in the y direction. Let's look at that one. And in the y direction, the y is opposite of the angle, so that would be sine, and the sine is opposite over hypotenuse. And in this case, the opposite side is the force tension in the y direction over the hypotenuse, which is the full tension force. Again, multiplying by Ft on both sides gives us that Ft times the sine of theta will be equal to the y component of the tension. So now, as I sum my forces in both the x and y direction for this system, I need to take into account that this tension force is both pulling over and up. So let's do an example. So we have a 20 kilogram block pulled to the right by a force along a cord of magnitude 40 newtons. The cord is at an angle of 30 degrees to the floor. The box moves at a constant speed. So in looking at this question, there are a few things that I notice. I have the mass of the box, not the weight, but the mass. The force along a cord, that is a tension force. And magnitude means number, okay? The word magnitude is just a fancy word that means amount or number. And then I also know that the cord is at an angle of 30 degrees to the floor. And I also know that the box moves at a constant speed, which means that it is in equilibrium. So now I can look at the question, which is, what is the magnitude of the friction force on the box? So the first thing I need to do is draw a free body diagram. I'll have the weight force straight down, the normal force straight up. The tension force will be up and to the right, and the friction force will be straight backward. So now that I have drawn my free body diagram, I can sum the forces. The net force in the x direction will be 0. Now if I look at the x direction, that's the horizontal direction along this dotted line here, I have a tension component that is in the x direction minus the force of friction. That would equal 0. Now the friction is a kinetic friction, because it is moving at a constant speed. If I sum the forces in the y direction, they're also balanced. Now the difference here is that I got a little more than just normal and weight in the y direction. So I've got the normal force up plus a component of the tension in the y direction and minus the weight. Those are the forces in the y direction. My question asks me to find the magnitude of the friction on the box. Well, here is the friction. So in order for me to determine this friction force, I'll need to determine what the tension in the x direction would be. So if I go back to how we have defined the tension in the x direction as being Ft times the cosine of the angle, I can make that substitution into my equation. Now if I'm looking for the force of friction, the Ft cos theta, add F friction to both sides, and now I can make my substitution because I know that the magnitude of the force is 40 newtons and the angle is 30 degrees. This gives me 34.64 newtons is the force of friction. So let's look at another case where we have a 30 kilogram sled pushed with a force of 40 newtons directed 30 degrees below the horizontal. So what would this look like? Here's the ground, and then here's our sled, and our sled is being pushed on at a force of 40 newtons but directed at this angle below the horizontal. So if the horizontal is here and the pushing is happening below the horizontal, then we have to be careful to treat this force appropriately. So let's find the force of friction. So what is the force of friction on the sled if it moves at a constant speed? Remember, that'll mean that it's in equilibrium. Now the first thing you always do is draw a free body diagram. And in this case, we would have, of course, the weight. The earth is pulling down on the box or the sled. The surface is pushing up on the sled. Now the person is pushing into the sled, so along this line here. And so when we draw the force that I've just highlighted here, we draw that force there on our free body diagram. We draw it coming from the object and away. So notice that this arrow here, this force push, is the same as the force that the person is pushing, that's down and to the right, but we're just drawing the section of it that is leaving the box. And then there would be a friction force backwards. Now we have the free body diagram of all the forces acting on our object. We can analyze these forces and create the force equations and solve for the force of friction. So, because it is moving at a constant speed, the net force in the x direction is 0, and the forces in the x direction would be a component of the pushing force. So force push x minus force friction is equal to 0. And then likewise, we can sum the forces in the y direction, and they are also balanced. and we have a normal force that is up, a weight force pointing down, and then part of our pushing force is actually in the negative direction because we're pushing it over in the right direction, but down in the y direction. So I'm going to call this F push in the y direction, and it will equal 0 as well. So we're looking for this force friction that is right here in our equation. So let's solve for the force friction there. So I'm going to come over here and write force push in the x direction is equal to the force friction. I just added the force of friction to both sides. Force push in the x direction will be equal to force push times the cosine of the angle, just like we've done before, and that will equal our force of friction. And this is a kinetic friction because it's moving, so we have to keep up with that. So then we have a 40 Newton force at 30 degrees, and the force friction kinetic is again 34.64 newtons. My next question is, what is the coefficient of friction? So what is mu? Kinetic. So if the force friction is equal to mu times normal, then if I can find my normal force, which was in this equation up here, and I have the force friction, then I should be able to find my coefficient of kinetic friction. So let's start by finding what is the normal force acting on the system. So I'm going to go over here, and we're going to write this down as the force normal would be equal to, I'm going to add Fg to both sides and add force push in the y direction. So then my normal force will be 30, the mass, times 10, because remember the gravitational force is m times g, and then we're going to add the force push, which was 40 newtons, and then in the y direction would be the sine of 30 degrees. So that means our normal force is equal to 280 newtons. So let's take this and substitute it back in over here for our normal force. So we've now got both pieces that we need. So we have 34.64 is equal to mu kinetic times 280. So mu kinetic will be equal to 34.64 divided by 280, which gives us 0.123 as our coefficient. And remember, the coefficient of friction does not have a unit. And so now I know what the coefficient of friction is between this sled and the ground as it's pushed with this force of 40 newtons at an angle of 30 degrees below the horizontal. So the first step was to create your free body diagram. The second step was to sum the forces. The third step was to use the equations and solve.